Again, in this lecture I wanted to give you a little bit more technical thing. It is derivative estimate of harmonic function. So, first of all, consider a ball, with center x and radius r. And I wanted to find the function which is delta u equals 0 in, let us denote it by d. d, it is gamma equals s of xr. And u on gamma equals g. So it is a solution of this Dirichlet problem. Unlike the general Dirichlet problem, where we have here arbitrary domain and arbitrary, here we have not zero but something else, and so on, we know solution of this equation, of this problem. It is u of x equals integral over s of xr of what? H xy, let point x here, u of y dsy equals integral s xy, u on the gamma, y is on the boundary, equal g h of xy u g of y dsy. So hxy is the Poisson function, or it's called Poisson kernel, h of xy equals 1 over r omega n, r square minus module x square divided by x minus y to the power n. Omega n is the area of the sphere S. So it is a sphere of radius r in the Rn, so it is n minus 1 dimensional area. So I want to find the derivative of this h, because let us write, if you differentiate this with respect to x, so it is gradient u of x equals integral over s of xy, gradient with respect to x h of xy, let me write u of y dsy. Yes? So to find gradient u, we have to find gradient h of xy, where h is this function, r and omega are constant, so it is not a big deal to find its gradient. And then we can substitute here and extract different implications from this. So let us write gradient h of x, y, gradient with respect to x. So y is parameter for any y. We have to differentiate this. Now let us differentiate. Equals 1 over r omega n. It is constant. X minus y to the power 2n. So it is x minus y to the power n times gradient of this with respect to x times minus 2x. Gradient of x squared is 2x. X is a vector. You know what, let me put here the point O. It is the origin, so that x is identified with the vector from O to x. So it is first minus r square minus module x square times derivative gradient of this times n module x minus y to the power n minus 1 times gradient module x minus y. It is x minus y divided by module x minus y. Yes? Because gradient of module x is x divided by module x. Let me write here. Gradient of function module x, length of x, equals x divided by module x. You can do it if you write module x as square root x1 square plus x2 and so on. We did it, I think, more than once. Equals, okay, so now we are interested, no, it is the formula to make it simpler. Let us find it when x is 0, so at this point, at the center. Gradient x h of 0 y equals 1 over r omega n. So x is 0. So the first term is 0 because 2x is 0. So I don't write the first term. X is 0, x minus y equals r. So it is r to the power 2n, and here r square module x square times n times r to the power n minus 1 divided by x minus y minus 1 again times minus y, and here was also minus. So it is equal to r to the power, in the denominator, minus 1 to n plus plus 1 minus 2 minus n plus 2 omega n, and here minus n y to n, so n plus 1. So let me write it again. Minus, no, plus n. Gradient with respect to s, h of xy when x is 0 equals ny divided by omega n r to the power n plus 1. R to the power n plus 1. Module gradient xh of xy when x is 0 equals, no, model y is r. So let me draw here. It is O, it is x, x is here, equals x here, y, it is s 0 r. Equals n omega n r to the power n. And now let us find gradient u of 0 equals integral over s 0 r h of 0 r u of y gradient over x h of 0 y dsy. Yeah. Now, if you now let us do the following. Let us estimate module gradient u of 0. Now we estimate this integral. Maximum module u of y in s of 0 r, yes, times module gradient n omega n r n times the area of the sphere. Area of the sphere is omega n is the area of the sphere with radius 1, and area of the sphere of radius r is omega n r to the power n minus 1. which is equal to n divided by r maximum module u of y. I write module y equals r. Interesting and simple formula. Once again, let me repeat it here because it is important. Module gradient u of 0 less or equal than n over r maximum module u of y such that module y less equal r. Now we can also shift this, put this center not at the point 0, but at the point x. And this is S of xr. And then you have module gradient u of x at the point x less or equal than n divided by r maximum module u of y. Y is S of xr. Now, it makes sense if the function u is harmonic, no, at least inside this ball B of at the point center x and radius r. Yes. So this is the simple formula. No, they can also write it in more general form. Suppose we have a domain D, boundary gamma, and U in C2 of D, intersection C of D bar. D bar is D including gamma. And then we have a function, Laplacian U is 0 in D. So the same situation, harmonic function inside domain, and it behaves reasonably well when you approach gamma, at least it's continuous here. And then let us take any point x and consider the maximal ball such that it is inside domain D. Maybe it touches at some point or in some points the boundary of D. Yes, so its radius r equal the distance between x and gamma. Yeah. And the function is harmonic inside this ball and continues up to the boundary, and so we can use this estimate and have that gradient u at the point x less or equal than n divided by r maximum module u of y So where? No, if you want to have only estimate which depends on the value of the function on the boundary, so the function inside is less or equal than the function on the boundary, maximum model of the function. So you can write y in gamma. Yes? N divided by r equals n divided by distance from x to gamma, maximum module u of y, y in gamma. Yes? No, similar estimate we have for higher derivatives. If you differentiate this function h more and more times, then we have the estimate of the following form. Let me write. Let me take the partial derivative d alpha u dx alpha. What is alpha? Alpha equals alpha 1 alpha n. Yeah, it is how we write the partial derivative. Alpha 1 times along x1, alpha 2 times along x2, and so on. So it equals d modulo alpha equals alpha 1 plus and so on, plus alpha n. This simple notation, d modulo alpha u dx1 alpha 1 dxn alpha n. No, not all alpha k are positive, some are 0. If it's 0, no, simply it is absent here. And we write d alpha u dx alpha, yes, less or equal than some constant c depending on module alpha of module alpha, no, some constant divided by distance of x from x to gamma to the power module alpha. Yeah, here module alpha is 1, it is the first derivative, so we have distance to the first power. So I don't think it is wise to derive this formula times maximum module u of y, y in gamma. So this is the general result. No, this c, we can estimate this c, but I don't see necessity at this moment. Simply I would stress that derivative of any order of the function u in our domain, inside domain at any point, is estimated through the values of u without any derivatives on the boundary. If you studied the complex analysis, then there was a similar estimate which is called Cauchy estimate, and simply in complex analysis it is more, I would say, in a more beautiful form. It is not so general like here, but it is a more neat and compacted, beautiful form. So we have this estimate, yes, and the first A consequence of this, no, the last today, is what is called Liouville's theorem. Liouville's theorem says the following. Suppose delta U equal 0 in the whole Rn, and module U of x less or equal C for all x in Rn. So the function U is harmonic and bounded in the whole Rn. Then U of x is constant. The only harmonic function which is bounded and harmonic in the whole Rn is constant. Yes, sir. Again, very probably that you have learned similar theorem in complex analysis, that any bounded, everywhere bounded analytic function is constant. They are similar and proved similarly. Now the proof will be here. Let's take any point x. So module gradient u of x, yes, less or equal. What is little n? Divided by distant x gamma maximum module u of y in gamma. So now what is gamma here? No, as the function is harmonic everywhere and defined everywhere in the whole Rn. So we take as gamma, it is x, and gamma equals s xr. So it is less or equal n divided by r, and maximum y, model y, is less than some c. Yes, the function is bounded by c everywhere, in particular on this large sphere times c, and c divided by r. R is arbitrary large, yes, for any r. So if it is true for any r, so n and c are constant, r can be arbitrarily large, r is in denominator, so this means that module gradient u of x equal 0. That's it. So the Liouville theorem, there exist different generalizations of Liouville theorem. Say if the harmonic function is defined in the whole space and grows not very fast, say like module x to some power k, yes, then in fact this function is a polynomial of degree k. Say if it is bounded by module x plus some constant, then this function is just linear function. It follows from these estimates. So we simply prove that some all derivatives of partial d of some order are 0. If derivatives, say, of order 10 are 0, then our function is polynomial of degree 9. That's it. That's it for now. And we will need such estimates, simple estimate, in the last topic of this section. It is existence of solution of the Dirichlet problem. So this is what I will do next time. For now, let's finish. Have a good time. Bye.